Okay, guys, we're going to move on to 6.2, acceleration of gravity and orbital velocity. We're going to do a real quick review of Newton's law of gravity, then we're going to talk about the acceleration of gravity, and then we're going to talk about circular orbits and how we achieve orbital velocity. We start with our quick review. We have a mass. We'll call this M1. And we have another mass over here. We'll call this M2. And mass 1 exerts the force of gravity on M2. And when you have these two masses, they're going to exert a force on each other. And the forces are equal to each other, and this is the force of gravity that they're each going to exert on each other. And the force of gravity between them is equal to our universal gravitational constant. It is proportional to the mass of the first one. It is also proportional to the mass of the other object. And it is inversely proportional to the square of the radius between them. And this also has this little negative r hat in there, and this just means that this is an attractive force. Okay, so if this direction is r hat, then we've determined that if we go from M1 to M2, then the force that M1 has on M2 is this guy over here, where it's pointing back towards the radius. So that's what the negative r hat is talking about. And we know that G, according to a great experiment by Cavendish that we covered in the last lecture, G equals 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, which is an exceedingly small value. And it makes gravity, it's a very, very weak force. However, it's a very important one because it deals with large masses, and you really start feeling it when you have these large masses. Okay. Now, we do know from way back when that the Newton's law, Newton's second law, is that the sum of the forces. Okay, so we're going to take a look at this one right here. Okay, and then what's the force acting on M2 right here? And that the sum of the forces on M2 equals mass times acceleration. Well, if the force acting on it is this gm1 m2 over r squared, then this is what also equals mass times acceleration, mass 2 times acceleration. Well, in this particular case, the m2's can cancel, and so the acceleration on 2 is equal to g times the mass of the first thing over r squared. And then similarly, the mass of the acceleration on the first object is going to equal g m2 over r squared. And so what we get is this idea that g, if we have this acceleration due to gravity, 9.8 meters per second, g is going to equal m, well, g of course, times m, over r squared. And close to the surface of the Earth, if you close to the surface of the Earth, if this becomes the mass of the Earth, this is going to equal 9.8 meters per second squared, and you can actually plug it. Oh, there you go. And you can actually plug everything in, and you'll see that this times the mass of the Earth divided by radius squared equals 9.8. This is also how we determined what the mass of the Earth was. So we could we knew the size of the Earth. We knew we figured out what g was, and we knew that things fell at 9.8. So we could figure out, oh, hey, the Earth's going to be about 6 times 10 to the 24th kilograms. All right, this brings us to circular orbits. All right, so let's say that we have a big we're all riding here on this big blue marble. No, almost a beautiful circle right there. I needed a little more curvature right here. Okay, this Earth has mass m. Okay, and let's say an object is orbiting our planet here. Okay, it has this orbit, and it's got a mass of m, which is directed, and it's got a centripetal force with the force of gravity equals g m over r squared, and because that r hat just means it's pointing towards the center again. Okay. Now, the acceleration then, okay, if this accelerates, we know that, and that this force equals, because it's a centripetal acceleration, this force is equal to mv squared over r for this particular satellite. Now, okay, and this, remember, is the mass of the, let's move that over. This is the mass of the satellite. All right, so that m is this m. Okay, those are the same. All right, so if we want to see how fast it has to go for any particular radius of orbit, then this is a really easy solve, that our m's will cancel each other. Okay, and then we get v squared over r equals g big M over r squared. Okay, this is going to turn that into a 1, and then we get our v is equal to the square root of big G big M over r, and that is our orbital velocity at any particular time. Okay, now how fast? Okay, so here's my question, and here's how fast we have to go. How exactly, how fast is this? So, okay, we're back on our planet here. We have our planet Earth, and we're going to draw this. I'm going to draw this kind of small here. The planet Earth is a pale blue dot. All right, and on this planet Earth, we're going to get way in there. On this pale blue dot, let's see if we can get it well focused. It's not liking me here. Find it, find it. Where are you? Oh, there we go. All right. So, and here you are firing a cannon. Okay, and you go, and you fire the cannon, and it falls to there. Okay, and then say, oh, that was cool, but it didn't go real far. So we're going to fire it. We're going to put a little more gunpowder in there. We're going to fire it again, and it's going to go, and it's going to go around. It's going to follow the curvature of the Earth until it gets to there. And there were actually, during World War II, we had battleships that could launch projectiles that were the size of Volkswagen Beetles. They were 1 ton. They were 1 ton shells that they were launching beyond the horizon, and so they couldn't actually see what they were firing at. They had to have planes flying over and radioing back, telling them, oh, okay, you missed it by about this much. You missed it by that much. Then that was pretty cool. Then we go, and it makes it almost all the way around until we hit it hard enough to, no more March of the Penguins. We destroy the. All right, and then that was pretty cool, but we're still not there. We go one more boom, and we hit it so hard that it comes around and then we get out of the way. But we hit it so hard that it comes all the way back around.
Report to the main office. Shabria Mitchell, Matt Renfro, Haley Schwartz, Bailey Harrell.
Goes all the way around to the point where the velocity at which we have launched our projectile is curving towards the surface of the Earth at the same rate that the Earth is curving away from it. Okay, and when that happens, you have reached orbit. Okay, and at any particular radius above the surface of the Earth, or any particular radius above the center of the Earth, okay, you have that particular velocity that you have to reach. Now, this does not work on the surface of the planet because we have a because we have an atmosphere. Okay, so I'm going to use my drawing skills here and create an atmosphere above the surface of the planet. It's kind of hazy, particularly if you're in Central California. You know, this hazy atmosphere. All right, so we're going to say that this point we're going to say that this point right here is Florida. And in Florida is where we have Cape Canaveral, and this is where we launch things. And so when we launch things, we launch them upward, and then we give them a pitch. But we need to go upward first and then pitch them, because we need to get out of our atmosphere as soon as possible. In fact, there's a spot right here, well, right about there, where the atmosphere, the spacecraft that you're launching is going so fast that the atmosphere reaches what's called maximum dynamic pressure, and it's a combination of the speed of the it's a combination of the speed of the rocket, the acceleration of the rocket increasing so much, as well as the atmosphere pushing on it, that the speed's getting faster, and the atmosphere is getting smaller, and so we have this moment of maximum pressure, and then it dies off. But once it dies off, then we start accelerating in this direction to build our speed so that we can curve around the Earth. And so then we get our, then we get things like this. Again, you may recognize this. This is our space station. Although it kind of looks like a cheerleader with a really funny headdress. But anyways, that's what it's supposed to be, our space station, and it is orbiting at a particular height above the surface of the Earth. And so what we have, if this is h, okay, then we have and this is about 300 kilometers above the surface of the Earth. And so what we're going to do is we're going to figure out how fast the space station orbits the Earth. And so we know that our velocity equaled g m over r squared, okay, where this is the mass of the planet, okay, and we know the radius of the Earth, but this radius is not just this height. It is this height plus the radius all the way down to the center of the Earth. And so that's going to be our r is going to equal the radius of the Earth plus the height above the surface. All right, so what are these things? Well, if we've got the radius of the Earth equals 6.37 times 10 to the 6th meters, and the height is, if it's 300 kilometers, and that's 3 times 10 to the 5th, but we want to get into the 10 to the 6th, it's going to be 0.3 times 10 to the 6th meters. That gives us a total of 6.67 times 10 to the 6th meters. The fact that this is 6.67 and g also starts with 6.67 is an artifact of coincidence. There is nothing, they have nothing to do with each other, it just happens that way. All right, so we're going to figure this out, and once we get our v is equal to the square root of, and this is a lot of numbers here, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times mass of the Earth, which was 5.98 times 10 to the 24th kilograms, all over 6.67 times 10 to the 6th meters. And we square root that big, oh, I'm sorry, this should not be squared. Okay, so we square root this bad boy, and we get, let's figure this out. Let's plug this in here, and we're going to get, let's see if I have room for this on here. So we're going to get 6.67 times 10 to the 11th times 5.98 times 10 to the 24th divided by 6.67 times 10 to the 6th meters equals, and then we square root all that, and we get 7,733 meters per second, which if we convert this to miles per hour, and I used to know what this is, I did it earlier, this winds up being approximately equal to 17,300 miles per hour. And at this point, you could use 2 pi r and figure out how far our spacecraft travels, okay, in any orbit. Yeah, so here's your radius of the whole thing, and how far did that, 2 pi r times that is going to give you your total circumference, and then divide that by your 17,300 miles per hour, and you can figure out how long it takes for it to take the round trip. And it winds up that it takes about 1.5 hours to circle the Earth. All right, so real quick review. That was the force of gravity equals mg, but as far as we're concerned with planetary gravity, we have g mm over r squared equals mv squared over r, and from this we get that our velocity equals gm over r, and that's our orbital velocity. And that's it for this one, and we'll see you guys next time.